Alright, welcome back to Meteorology 101. In this video, we're going to cover thermodynamics. Visit my website, meteorology101.com. A lot of info over there. And please comment on these videos if you have any questions. So, let's get started. Thermodynamics, pretty much what we get out of a sounding is, and weather observations. We covered weather observations in the last video, and all that's put into a computer program, and we get the big picture of what's happening with weather systems. So with thermodynamics, we use those tools such as a sounding to get the upper layer charts, and we may jump into them if we have time, but we're going to try to stick to the course. So soundings, the thermodynamic tools that help weather forecasters answer the questions of what's going on in the local atmosphere. When they let a weather balloon loose, the radio sound goes up, sends back data, mandatory levels, and then it has the option to send back essential data at any level in between. So the mandatory levels are 1,000 millibars, 925 millibars, 850, 700, 500, 400, 300, 250, and 200 millibar levels. So anywhere from 364 feet, that's 1,000 millibars, to 38,662 feet if the balloon makes it that far without popping. As a low approaches, we want to know, based on the atmosphere, is there a chance of rain, freezing rain, or snow? You can get all of your precipitation types off of these charts, and how much of the air mass basically has modified when it's moved out of its source region. So if there's a continental polar air mass pushes down from the north, then how much moisture has it encountered? How much has it warmed from below that modified that air mass as it pushes south? And when these soundings are let go, it's every 12 hours, so there is a gap, but there are forecast models that develop these soundings too, and all that data is extrapolated onto these charts, and then you can analyze these charts and pull up your energy levels, your cloud heights, based on lifting an air parcel, cloud heights based on just heating an air parcel and causing it to rise, what layer, at what level is the clouds going to form. So there's a lot to these charts. So phases of matter, matter exists in three primary phases. The matter we're going to be focusing on is water for the atmosphere. Solid, liquid, and gas are the three phases. So in the solid state, molecules stay in a fixed state and have a low energy level. So think of it as how fast are the molecules moving as water is in each different state. If it's frozen, it's cold, it's not moving around much, so it's a low energy level. Liquid state molecules move around, but they remain cohesive and maintain a constant density. And then in the gaseous state, molecules are independent of one another and move in any direction, and they have a very high energy level. Okay, so in meteorology, we talked about, we deal with phases of water. So solid is ice, liquid is water droplet, gas is water vapor. So in each phase is favored at a specific temperature. So we know that the freezing or melting of water is 32 degrees Celsius or 32 degrees Fahrenheit or 0 degrees Celsius. Boiling point of water is 100 degrees Celsius or 212 degrees Fahrenheit. So that is our mixing, melting and freezing levels, and our evaporation and condensation levels. So going back and forth. Now, the one we're most familiar with is going from a liquid to a solid. When the temperature falls, then water starts to freeze. We got the ice on the ground, we got the snow, and then at what point that the water is converted to ice. That is the most common phase that we think of. Above that temperature, it will become a liquid, and if we continue to heat it to its boiling point, then it becomes a gas. So collisions of molecules are always taking place, and there's such a small portion of molecules that are knocked into high energy state they escape to a gas. So water does not have to reach its boiling point to escape to a gas, to become a vapor. So it doesn't have to hit that 212 degrees or 100 degrees Celsius to actually become a vapor. So you'll have steam actually well before the boiling point of water. To ascend in a higher energy state, such as a liquid to a gas, the molecules absorb energy. So think of when you're going from that solid state, ice, to liquid, you're absorbing heat. So the water droplet warms up, becomes a liquid, or the ice cube absorbs heat, becomes a liquid, and then that water droplet absorbs heat and then finally evaporates. So when descending to a lower energy state, then the release of energy is required by the molecule. So it's the opposite. When you got gas, you got a high energy state, molecules are bouncing off of each other, it's hot. Once it starts to cool, those molecules slow down, so it reaches a lower energy state to become a liquid. Then it starts to condensate into a liquid. But just remember, in clouds, you have to have something for that water to condensate to. And that is the release of latent heat. In meteorology, when it releases that heat from a gas to a liquid, it's releasing heat, so that heat goes into the atmosphere and actually warms that air mass. So that's when we talk about the air mass moving over, a cold polar air mass moving out of the north, pushing south. It's moving over that warmer air, and then that warm air getting absorbed into the colder air and creating a higher energy state there, but actually heating from below. So it will modify that air mass. So the release of latent heat, very important in meteorology. When you think of water, it's actually raining. If you've ever seen it rain and it's evaporated before it hit the ground, that is virga. Then that energy is released into the air around it, and actually evaporation is a cooling process, so it will actually cool that air mass. And these processes are what's mainly responsible for heating or cooling weather systems within our area. Okay, so when we talk about lifting an air particle or forcing an air particle down, there are several types of lift: frontal lift, orographic lift, heating. So when we force an air particle up, like the orographic lift in this picture, when we start to force that up, it's a dry air particle. It's not rain being forced up the mountain, it's air. So that contains water vapor, but it's pushed up. The temperature of that air particle starts to cool, and it will cool at 10 degrees Celsius every 1,000 kilometers. So as the air particle rises, eventually the temperature will drop to the dew point and cause condensation, and then that's the level at which the clouds will form. So when we talk about the Skew-Ts, the lifting condensation level, the convective condensation level, how an air particle is forced up depends on where a cloud layer will form. So the air particle rises, expands, cools. The molecules take a lower energy state, achieve a lower energy state, and the rate of cooling is given by the dry adiabatic lapse rate until it reaches condensation. Once it reaches condensation, then you have to rise that air particle moist adiabatically after that, and that's a different temperature, because remember, you're warming that atmosphere by it cooling but releasing the latent heat, so it's heating the air around it. So now it's approximately 4 degrees Celsius difference on that. So as we go up in the forcing this air particle up the mountain, we're dropping 10 degrees every 1,000 kilometers, or every 1 kilometer, it'd be 1,000 meters. Every 1 kilometer, 10 degrees, until the temperature reaches the dew point and condensation occurs. And then it's going to drop 6 degrees every 1,000 kilometers after that. Once that air particle gets over the mountain and starts to descend, then you're going to go moist adiabatically until the saturation, until the water evaporates, and then so it's going to be back to the 4 degrees. And what you end up with is 10 degrees every 1,000 kilometers after that, and then you'll end up basically at the same temperature you started with when you started to rise. So the air partial will go through that complete process and end up right back where it started. Okay, so release of latent heat. If an air particle cools to its dew point, then it achieves saturation. We just talked about that. A cloud forms. Any further lifting will cause condensation in the form of water droplets or ice crystals. So once you reach the point of saturation, then it has to, like I said, it has to have something, dirt, salt, dust, something to condense to in the atmosphere. And then that's when the water droplet forms. Or the ice crystal, depending if you're above the freezing level or not. Then you have an ice crystal, say a cirrus cloud, 20,000 feet up, you're pretty much always above the freezing level. Then you'll have a cloud made up of ice crystals. Anything below the freezing level, you'll have a cloud made up of water droplets. So the phase change, by its very nature, releases latent heat. So you're cooling, so you're releasing heat. So you have to be releasing heat to cool. Now, the heat is released into the air partial, and the air partial begins to warm again. So once that condensation takes place, you're releasing latent heat. Now the air partial itself, that column of air, an air partial is just an imaginary cube of air that meteorologists use to put things into perspective. So it's not like any certain measure of how much air, this is happening with. It just depends on. This is just to project the image of, okay, an imaginary cube of air rises, cools, condenses, and releases that latent heat. All right, so back to that chart that we were at. A partial which is lifted 1 kilometer will be 10 degrees warmer from the release of latent heat. Overall cooling rates from 10 degrees to 6 degrees per kilometer. Once, like I said, once it reaches saturation, once that temperature drops to the dew point, then that heat has been released. Now you got a 4 degrees difference on a moist adiabatic lapse rate than you do the dry adiabatic lapse rate. So as lifting continues higher into the troposphere, less and less latent heat is released due to the dwindling amounts of moisture in the partial. So you're running out of that moisture as that heat is released. The actual moist adiabatic lapse rate becomes much larger at that point. So how does this affect the weather? Let's get into that. Let's cover subsidence, but like your lapse rates, your typical lapse rate's about 6.5 degrees per 1,000 feet. It's 10 degrees on a dry adiabatic level, 10 degrees per 1,000 kilometers, 1,000 meters, and then 6 to 6.5 degrees after that. So when a partial sinks or subsides, then the pressure rises and the molecules are packed closer together. So that heats that air. So like think of the Santa Ana winds, when they come down the mountain, they're actually compressing and warming, and you will actually have warmer temperatures on the surface with the wind that comes off the mountains. Even though it's a colder air, it will actually compress enough to warm and create that warmer condition on the surface. So if an air partial is 30 degrees and has risen 3 kilometers, it will cool 20 degrees. And if we force it back to the surface, it returns to its original 30 degrees. So that's the picture we painted on with this orographic lift, is what basically where that temperature starts is pretty much where it's going to end up on the lee side of the mountains. Okay, so if condensation occurs at some point, the liquid droplets are present in the partial sinks and warms, and the droplets or ice crystals evaporate back into the partial, back into the air, and no longer it's no longer in a saturated state. So that's when it starts to dry out. So as it descends, it actually releases the moisture back into the air, and then it's no longer saturated. It actually becomes a vapor at that point. So it's a higher energy state. All right, environmental lapse rates. This is the typical layers of the atmosphere. Temperature change of the actual atmosphere with height is what the lapse rate is. Buoyancy and stability are determined when we consider the relationship of dry adiabats and moist adiabats with the environmental lapse rate. So the environmental lapse rate, like I said, is typically about 6.5 degrees per 1,000 meters. So we live in a troposphere. Typically, temperatures decrease with height, so we have a positive lapse rate. Then once you hit the tropopause, then there's no change in temperature, and then there's an increase in temperature. It's a stable atmosphere in the stratosphere. So as far as stability, actually we'll get into stability here in just a few minutes. Cold air over warm air is an unstable environment. We live in a troposphere. We go up in height, it's cold. The cold air continuously wants to sink. So just think of, we're always in an unstable environment. So here's stability versus instability. Cold over warm is unstable because cold air wants to sink. If you push that air partial, cold air partial, it will continue to move in that direction. So we push this ball off the bowl. Cold air wants to sink, it's going to continue to sink. Warm air, if you push the warm air up, it's going to, in a stable environment, if the warm air is already up and the cold air is down, you push that warm air up, it's going to go right, stay back, continue to rise. So you're in a stable environment. Warm air wants to rise, cold air wants to sink. They're separating, no mixing going on. Cold air wants to sink, warm air wants to rise, so you got a lot of mixing going on, so you're in a stable environment. Now if you push an air partial and it stops or returns to its original position, then you're in a neutral environment, which that does happen too. So all right, so the soundings, it's a graph of properties of the atmosphere such as temperature, dew point, in respect with that altitude. So they let the balloon go, radio sound sends back all the data. We used to plot these Skew-Ts. The Skew-T log P diagram. We used to plot these by hand. The computer does pretty much everything for you now. So that chart was invented in 1947 by meteorologist and physicist Nikolai Herlufsen, and was quickly embraced by the United States Air Force. So when we go to weather school, I was in the military for weather school. We went to the Air Force weather. They're the ones that did all the weather training. And we did learn how to plot a Skew-T by hand and then analyze it, all the different readings by hand. But like I said, now with the computers, all the programs out there, we don't have to really do anything by hand. They got rid of all of the DIFAX charts that used to print out from these weather balloons. And all that was printed out, and we would actually go through and analyze those by hand. And that way we got a more accurate forecast for our local area. So a sounding or Skew-T, this is the complete Skew-T chart. We'll go through these lines so you understand what they are. So you got the solid lines going diagonal, solid lines going horizontal. You got the green lines that are kind of skewed, and you got the green dash lines at an angle also. So if you look at these, this is pretty hard to see, but they're separated by green and kind of a pinkish orange. Those are every 10 degrees. So each section is 10 degrees Fahrenheit. So let's go look at these lines. The horizontal lines are solid lines. They're isobars, lines of equal pressure. This is based on a standard atmosphere. So there's a height scale on the left that indicates feet or meters, so you can use either metric or standard on this chart. The isotherms the lines of equal temperature for a standard atmosphere are at an angle, and those are the ones separated with color. So those are like I said, about every 10 degrees between those different colors. Each color section is about 10 degrees, is 10 degrees. The mixing ratio, the dashed lines are going at that angle. That's the mixing ratio lines. The dry adiabatic lines, those, if you look at those are kind of skewed up into the atmosphere. They're a solid line going from the bottom right, top left. Moist adiabats are a skewed line, green line going pretty much from the bottom of the chart and then skewing up to the left of the chart. And then that's back to the original completed chart. Alright, so what are all these lines doing for us? As we get the data comes in the code. I don't think I put anything in here on the code. It's you wouldn't understand it if you looked at it without something to break it down. I used to have most of it memorized. We used to plot these things every day, twice a day, so we could decode that just by looking at it. Couldn't do it anymore. But each time you get a reading, it tells you what level the balloon sent the reading back at, the radiosonde sent the reading, what level it was, what the temperature was, what the dew points was, and what the winds were on that at that level. So you plot temperature, dew point, and winds on each layer. So each one of them dots is a height that the balloon has sent data back. So every height you have a plot. The blue is the dew point, red is temperature, and then you have your wind bar. Now, these lines can change. You can go red, blue, black, black. It really doesn't matter because the dew point will never cross over to the right of the temperature. It will never be higher than temperature. It will be equal or less. So you always know that the left line is typically a dashed line when that's plotted out, but that line will always be to the left of the temperature. Instability. Now, one big thing on this when we get instability is we were talking about the lapse rates. Our typical lapse rate about 6.5 degrees per 1,000 meters. So we check how that temperature matches up with the dry adiabats or the moist adiabats, depending on the environment. Is it moist out? What's the are we saturated? Typically, for condensation to occur or saturation to occur, we're going to be typically within a 5-degree difference between the temperature and the dew point. So if there's a 5-degree difference or less between the temperature and the dew point, you can say there's significant moisture at that layer, at that level. So there's most likely clouds present. We will pull up one of these charts on a computer program I got, and we'll show you cloud heights and stuff like that, and a couple of different readings and what we get out of it. So if the temperature line leans far to the left with height, it indicates the layer cools rapidly with height. So you're cooling rapidly with height. That is a unstable environment. Because in our atmosphere, we always cool at height. But once you get past that 6.5 degrees, you start going to 7, 8, 9, 10 on the lapse rate, 10 degrees per 1,000 meters on the lapse rate, then you're getting into a pretty unstable environment. So if the line exceeds both the temperature lines, if it crosses temperature lines or the dry adiabats and the moist adiabats, then you can pretty much say you have an absolutely unstable environment. If it's that steep like this one where it's crossing both of these lines, then this is it's considered an absolute unstable environment. If it falls between the two, then it's conditionally unstable. So if this was slightly a little bit steeper, let me see if I have one on the next one. No, that's an inversion. Let me go back. So if it's between the two, then it is conditionally unstable, and if it leans to the right of the adiabats, the layer is stable. So if the temperature increases with height, we know we're in a stable layer. If we're going almost straight up, then we know we're in a conditionally unstable layer. And if we're sloping to the left pretty sharp, than we are in a unstable layer. Okay, so temperature leans to the right. This is a stable layer, so I did have it on here. So temperature increases with height. This is an inversion, so it is a negative lapse rate. The temperature increases with height, so you know you're in an absolute stable environment. Same picture. Inversions, that's where temperature is the same or increasing with height. So if the temperature actually rode with the temperature lines, which are right here, these solid lines, if that temperature rode parallel with that kind of gray looking line or to the right further, then you're in a stable environment. So the warm air is above the cold air. So the cold air is on the surface, you're increasing with height. You have warm over cold, so you're in a stable environment. Okay, the three types of inversions: a frontal inversion, radiational inversion, and subsidence inversion. So the frontal inversion usually shows an increase in humidity with height. Radiational inversion is caused by the cooling from below, making it very common on clear nights. And then subsidence inversion is caused by the warming from above, typically from downward motion. So like I said, when the Santa Ana winds come off the mountain, they fall, they compress and warm. So as you get that warming, you get an increase in temperature with height. The radiational cooling from below, you have a warm layer moves over a cold ground, and then it's cooled from below, so the temperature on the surface drops. So that gives you a warmer temperature in the upper atmosphere. Not real high. We're only talking a few hundred feet, or maybe 1,000 feet or 2,000 feet, but you have an increase in temperature with height, so that gives you that stable environment. That's mostly what causes the fog. You get subsidence causing the fog, or radiational cooling causing that fog, and then fog is a stratiform cloud on the surface, so it is a stable environment. All right, a frontal inversion, you'll see the temperature and dew point lines converge with height. Where both those converge with height, that is an indication of a frontal passage and causing that inversion. Radiational inversion is caused by cooling from below, making it very common on clear nights, like we said before, and a decrease in humidity in the inversion layer, and occurs only on the surface. So you'll see that warm air moving over a cold surface, cooling from below, the surface temperature drops, and you'll have that increase in temperature with height. And then the subsidence inversion, the way to tell the difference, it pretty much its appearance is identical to a radiational inversion on Skew-T, but more likely to exist aloft than on the surface. You'll see that in the upper levels. You won't see that on the surface. See, we're decreasing with temperature or height, then we start to increase with temperature. That's a stable layer in the upper atmosphere. You could have rain, everything down here with all this moisture, but this is pretty much going to cap that atmosphere. So in a situation like this, you can get radio signals a lot further because you have that capping going on, and radio signals will bounce off of that and then return to the surface, bounce off the surface, and you have a continuous wave going, and it'll travel out to a further distance. Same thing with noise. All right, so some stability indices that we get from this thing is a lifted index. Based on these values, how stable we are in the atmosphere. So if you want to screenshot this or something, I'm really not going to read all that. We're going to go look at the values here. So in a lifted index above 0, the atmosphere is stable, and a lifted index less than -6 is strongly unstable. It's strong instability. So looking at these indexes is one thing. It's one tool to use on this chart to determine the stability of the atmosphere. All right, the convective available potential energy, everybody's heard of this one, the CAPE. So your CAPE values, 0 to 500 is weakened stability, 500 to 1,000 low stability, and then 1,000 to 2,500 moderate instability. Thunderstorms are likely. 25 to 4,000, strong instability, widespread severe storms, and greater than 4,000, extremely unstable. You get large hail out of that. The the K index, if you take the upper layers, like the temperature at the 850 minus temperature at the 500, plus temperature, dew point temperature at the 850, and minus the temperature at the 700, the dew point temperature of the 700, then you end up with this value that gives you what you're ending up with. These temperatures in the upper layers like that is, do you have a cold over warm situation or a warm over cold situation? So if your value ends up being less than 20, there's no threat of instability, no threat of thunderstorms. 20-25 isolated, 26 to 30 widely scattered thunderstorms, 31 to 35. So like I said, there's no reason to calculate this. All these computer systems do it now. We used to have to do it manually back in the day, but now we don't. So figure out these indexes. Pretty much, like I said, the computer program will tell you everything you need to know. Totals, another instability tool to use on this chart. And low level jet, you definitely got to need to know if you have a low level jet. That's going to tell you basically, do you have a strong low level jet, moderate, or weak, because that's going to give you an idea of what your wind shear is on the lower levels. If you got a lower level jet, or 40 knots or greater at 850 millibars, you have a strong low level jet. So once you hit that level, then you have a surface low or a thunderstorm, and you have that low level jet feeding that thunderstorm or pulling the mass out of that thunderstorm, then you can have a very strong updraft, and you can have severe weather, tornadoes, because you have a low level jet present. So good to know if you have 40 knots at 850 millibars, right around 5,000 feet. All right, let's get into the soundings. So this is your typical Skew-T chart. This is the program. It's a Rayob software, a little bit pricey, but you can pull up Skew-Ts anywhere across the United States, and this software will analyze them and download the model data, so you can do forecasts, Skew-Ts also, and then try to pinpoint where your thunderstorms or supercells are going to hit, based on each station. So take some time to do all that, but as far as plotting these things, the computer plots everything for you, analyzes everything for you. We got a whole list of numbers on the right hand side with our all of our analysis and all of the indexes for possible severe weather, possible thunderstorms. We're going to touch base on some of these, but not all of them. Pretty much we get most of our answers over here, and on the left hand side for analysis, you get a dry microburst possible, storm character, and then if you got hail, wherever that black dot is, that's what you should expect at this time on this Skew-T. So no hail. This is a sounding for KMHX. It's for New Bern, North Carolina. It's close to the Outer Banks. So storm character, where that black dot is, ordinary cells. So if any thunderstorms popped up in this area right now, it would just be ordinary thunderstorm cells, nothing significant. So you can go multi-cells and then supercells. And then there is one area where there's crossover. So if that black dot got up into this area between those, then you could have multiple supercells. Chances of that happen pretty slim, but we'll cover some of these indexes, some of the analysis on this. So the trope level, it's off the chart, doesn't even show what the height, the troposphere, the top of the troposphere is, the tropopause. Freezing level, 13,996 feet. Now we can hit analyze, and then we can put, we got quite a bit of different things we can put on here, but we can do, pretty sure freezing level is on here, mixing height, freezing line right there. So now we know our freezing line is right around exactly what that says. 13,996 feet. So you can just get a visual on that. So you can see where your moisture is, how far your moisture goes up, and then, you know, say, hey, okay, if a thunderstorm pops up in this, we're probably going to have hail because we have enough moisture in those mid-levels to produce that. Now, hail would be a 1/4 inch based on this Skew-T. Water, atmospheric, how much water is in this atmosphere is 1.76 inches. If it were to rain, how much rain could you get out of it? Lifting condensation level, if we lifted a parcel by terrain or front, anything that gives us, you know, mechanical lift, then what our lifting condensation level is, and that's just what level the clouds are going to form if that air parcel was mechanically pushed up into the atmosphere. The CCL is the convective condensation level. So if just by daytime heating from the sun, the ground gets hot air rises, what level would it have to rise to create clouds? Now, in our analysis, we can do, we have clouds in here. So now we can see the different cloud layers that we can have, pretty much all the way up to 500 millibars, which is just over 18,000 feet. So it's probably about 18,000 because it's just below the 500 millibar level. Just above 400 millibars is over 23,000 feet. So we have some high clouds, and then the 25,000 millibar, 250 millibar level, that's 33, right at 34,000 feet. So could have some clouds in that level too. So based on just looking at clouds. Now, we can analyze our lifting condensation level. Basically, you take the surface temperature, just follow the dry area back up, and then you take your dew point surface temperature, your dew point, and follow that moist area back up, and where they hit is where you're going to have your lifting condensation level, or your CCL. Let's go look at the lifting parcel right there. It's pretty much right where there's a conversion, there's temperature and dew point. So this isn't a great example because it's pretty much already giving you the answer there. So I can back these off and open those up a little bit. I was using that one for a more or less for a severe look at some severe weather, but not really any severe weather on that chart. Just wanted to show you the Cape and go through some of those indexes. Let's go back forward to this thing. So I want to try to get that that lifting condensation level where it's a little bit more visible. It's pretty moist, been pretty moist on the surface, it looks like, in North Carolina. So alright, so you can kind of see it there. Alright, so that one ain't working out too good. It's pretty much staying moist close to the surface over North Carolina for a little while. Let's get back to one we want to see. I want to see the Cape index. The Cape is one that most forecasters use for severe weather. What's the energy? It's a measure of energy in the atmosphere. We're looking for 1,000 to 2,500 joules to be moderate thunderstorms. 25 to 4,000 to be widespread severe thunderstorms, and then a greater than 4,000 extreme and large hail producers. So let's get to a point where we can see that. Basically, that lifting condensation level, once you start seeing that on the right side of the temperature, is pretty much where you're going to have your Cape. So we got right there, it colors it in. Positive Cape, negative Cape, so our energy all down through that, all through those mid layers. Looking at the value, we got 477 joules. So we're not even close to being anywhere for any kind of thunderstorms or severe weather on this thing. All right. But you look at our cloud layers, you can see all the moisture, how close these temperature and dew point lines are together. So you got moisture all the way up into the upper layers. So this actually forecasts out a METAR. So you're looking at variable winds at 4 knots with fog. So visibility would have to be dropped less than 5/8 of a mile to be considered fog. So your visibility is going to be down. Scattered at 100 feet. Broken at 20,000, broken at 37,000. Now, that's not going to be accurate, I wouldn't think, just because looking at this layer right here, about 600 millibars are probably about 20,000 feet. 700 millibars are about 10,000 feet. So you should see some clouds in those layers too. So this thing's broken 20, broken 37, whatever. That's, like I said, take that with a grain of salt on the cloud heights. Now, lifted index, the negative 2.8. So we look at their chart, and we got lifted index, negative 2.8. You're going to be a negative, 0 to negative 2 will be thunderstorms possible, good trigger mechanism needed. So you're going to have something that gives you the lift. You need 3 things for a thunderstorm: moisture, instability, and lift. So if you have the moisture and instability, you're going to have your lifted index, but you need a trigger. You got to have something that causes that lift. Negative 3 to negative 5, unstable thunderstorms probable, and less than a negative 5 is very unstable and is heavy to strong thunderstorm potential. So we're on the weak side of that, but we're going to have some sort of lifting mechanism to cause that thunderstorm to kick off. So the sweat index, there's a 183. That's another one we use. 0 to 299, a severe storm's not expected. So if we did get a thunderstorm pop up in this area, then we would not expect anything to be severe. Our base level, even our CCL, just from daytime heating, the clouds should be right around 3,974 feet. So we're just around 4,000 feet. Level of free convection is at 334 feet. So as soon as that convection, if it did kick off on the surface, and all it has to do is hit 334 feet, and it's got free convection to continue. Nothing's really hindering that. You got a freezing level of 14,000 feet. So raindrops would have to be pushed up that high from an updraft to get pushed up over 14,000 feet above the freezing level to create any kind of hail. Like I said, quarter-inch hail would be what we would expect off of this sounding. And then let's see what else we got. Totals 44.7, 44 to 50 general thunderstorm. So if a thunderstorm was a kickoff, it would just be your garden variety thunderstorm. KI is the K index. That one is 33.4, so anywhere from 26 to 30, or 31 to 35 scattered thunderstorms. So if thunderstorms popped up, you could expect them to be scattered, but nothing severe, nothing crazy. So that's what these are all used for. But I take a lot of those with a grain of salt. Not all that's going to hit every single time. A lot of other factors we're looking at. So let's do an analysis on this thing. Let's see what we got for. We can see the cape, where our cape is. We know we don't have enough energy for severe potential. Let's go contrails. Where would your contrails be? 20,000 feet or higher, or actually 200 millibars or higher. So that would be up 38,000 feet or higher. If you had aircraft in that area, they would leave contrails. Inversions, there's this looks like an inversion on the surface. Subsidence inversion at 568 feet above ground level. So this program does tell you what type of inversion you have. If we back this up and go, see if we could pull one where we get to an inversion. Right there's one. Now, analyze, go to inversion. There we got a subsidence inversion, and I can't tell what that is. Let me get rid of the clouds. 4,395 feet. So with an inversion that strong, definitely a subsidence inversion being elevated like that, you know, that would cap any of that moisture on the surface. And then, like I said, radio waves can travel through that a lot better. Noise can travel through that a lot better. So you'll get a lot further distance on radios. Another thing is low level wind shear. Do we have any? No, there's nothing. Actually, very at the surface might be a little bit of low level wind shear, but nothing significant on this chart. Now the cape on this one, we are pulling 6 joules. We don't even have any energy in that system. So in this atmosphere, so we really don't have to worry about all that. But if we gave severe weather, I'll start keeping an eye on that. Maybe I'll do a video on that. We'll pull this program and we'll start comparing it to real-time data, what's out there, and then start pulling some of these values and see how accurate this Skew-T really is. Alright, so relative humidity, should put a line somewhere, just puts it over here. Now let's go, one other thing we can do is close that out, go to display, soaring data, whatever our forecast max temperature is for the station. I'm not sure what that was. This has it at 76.8 degrees. Let's go 85. Then we can calculate. Now if we close that out, we can, when we put our mouse over this chart, we can see all our values to the left. So our pressure, height, mean sea level, temperature, dew point, relative humidity. So we want to know how high we are. So now when you see these things spread apart like that, you got a subsidence inversion in place, but you got a dry layer right above that. Anytime they start spreading out, you can count them as just dry layers. Now when they're close together, then that's where you got moisture. Go clouds again. We can see the clouds at that layer, clouds up at this layer, and then clouds at the lower levels. So and then the subsidence inversion we do got clouds at that layer too, being capped off by that inversion. Alright, frontal layer, I don't have that option just yet. I didn't purchase that one. Let's go back. Not what I wanted. Alright, so we can follow these up. You can actually, with this program, I think you can forecast. I think you can analyze what you want. I thought you can move these. I know on one part of this, I don't use this too often, but I need to get back into this thing again. You can actually move these temperatures and dew points. Maybe with the current Skew-T. Let's go pull the latest one. Open sounding. I got screens you can't see. All you can see is the base screen, but I'm going back into the list and pulling the latest sounding. Let's go to the 9th. 12Z would be the one. Probably the 10th at 0Z, but we're going to go. Let's go 9 at 12Z on the 9th. Okay, so now I can actually move these and say, okay, if my dew point increases at this layer, then we can say what happens. We change all of our values. And give us a what if on temperature decreased. So when we talk about an air particle subsiding, compressing, getting warmer, then we could say, okay, the mid-level temperature of that air should increase, by 4 degrees. So we can increase this, and then we can try to determine how this air mass is going to be modified, and then what kind of readings we're going to get out of that. So not an easy task, but it is possible with this program. The mid layers, if you got a moist air advection in the mid layers, and you say, okay, we know we're going to go saturated at these levels, then we can pull this over to get them closer to the temperature with these dew points, and then increase the dew point, and then start showing different readings. Cape's only 27 joules. We'd actually have to drop this way down to start increasing that. If I can grab them, they're a little tough to get. You got to get each dot. Alright, so it's not working right now. There's one. Now our cape went up to 412 from doing that. .484. So you can see, obviously, when you get closer together, more saturation through the upper levels, then you can, have a higher energy level. All right, so restore. It says restore to activate. I'm not sure how to do that yet. I'm going to open a sounding. Okay. Alright, so if we go look at our LCL, CCL, carburetor icing, thermal, low level wind shear. You got to have low level wind shear to have a tornado, so keep an eye on that. Now your wind speeds also, like these wind speeds right here, they're coming out of the northeast and then shifting over to the west and northwest, so they're backing with height, so that should indicate that there's cold air advection in the upper levels with the winds backing with height. Humidity, let's see, mixing height, lightning. Okay, so possible area of lightning. Mean sea level 16,000. What's above ground level here? We got 17,000 feet. So what's our freezing level? 13.9. So we can definitely have some hail causing lightning 17,000 feet. Alright, display for severe weather. That's all I'm on. Let me see what we got. We can go winter weather, fire, tropical, hodograph. Let me pull up a hodograph real quick. So we're looking for a nice curve on this hodograph. This thing's kind of all over the place, so I wouldn't expect a whole lot to happen here. We'd have to find a Skew-T. Well, I just closed everything out. Okay. Alright, so I closed everything out. I just hit download again, so I got to download every station across the United States. But I'm going to go ahead and end the video here and say thanks for watching. If you learned something, hit the thumbs up. And the next video, we're going to be covering upper air analysis. So we're going to get into some upper air charts and how to read those, and do some just some upper level, just reading upper level charts and telling what's happening in the upper atmosphere. So like I said, if you like what you see, hit the thumbs up and subscribe. Visit my website, meteorology101.com, and thanks for watching.